Every diagram of the solar system you have ever seen is a lie of omission, not because the planets are drawn wrong, but because the diagram stops almost exactly where the real solar system begins. Beyond Neptune, beyond Pluto, beyond even the farthest spacecraft humanity has ever launched, there exists a structure so vast that it makes the entire planetary region look like a single dot on a blank page. The Oort Cloud may extend nearly halfway to the nearest star, wrapping our sun in a sphere of trillions of icy objects so distant that sunlight needs over a year to reach its outer edge. You think you know how big your cosmic neighbourhood is. You do not. Not even close. If you want to see just how wrong our picture of the solar system really is, hit that like button and subscribe. Now, get yourself nice and comfortable. Let's begin. Close your eyes and picture the solar system. You already know what it looks like. You have seen the image 1,000 times. A bright yellow sun sits at the centre. Mercury huddles close. Venus and Earth follow in neat succession, then Mars. After a gap of tumbling asteroids, the gas giants appear, Jupiter and Saturn, then the ice giants, Uranus and Neptune, at the outer edge of the diagram. Maybe Pluto appears as a tiny dot beyond Neptune, and then the image ends. The background fades to black. The solar system is done. You have carried this picture in your head since childhood. It appeared on classroom posters, in encyclopedias, on the covers of science magazines, in every documentary you have ever watched about space. It is clean. It is orderly. It is satisfying. 8 planets arranged around a central star in a flat disk of predictable orbits. The whole thing looks like a tidy mechanism, a clockwork model you could hold in your hands if someone built it to scale. This picture is not wrong. Every planet in it is real. Every orbit is accurate. The distances between them follow the laws of physics precisely. But this picture has a problem so severe that once you understand it, you will never look at the solar system the same way again. The problem is not what the diagram includes. The problem is what it leaves out. And what it leaves out is almost everything. That familiar image of 8 planets around a star represents the innermost sliver of the sun's actual domain. It captures the bright, busy, well-lit core of a structure that extends outward into darkness for distances so extreme that the entire planetary region becomes a speck, not a small portion, not a modest fraction. A speck. The solar system you carry in your head is like drawing a map of the Earth and including only your living room. The map is technically accurate. Your living room does exist. But you have mistaken one room for the entire planet. To understand how drastically incomplete the familiar picture is, you need to take a journey outward from the sun and keep going long after the diagram tells you to stop. Start at the sun itself. Our star is a sphere of superheated plasma roughly 860,000 miles across, burning hydrogen into helium at temperatures exceeding 27 million degrees Fahrenheit at its core. Every second, it converts approximately 4 million tons of matter into pure energy. This energy radiates outward in all directions, bathing the surrounding space in light and heat. The sun dominates its local environment so completely that everything within its gravitational reach orbits around it without exception. Mercury, the closest planet, circles the sun at roughly 4/10 of an astronomical unit, where 1 astronomical unit equals the average distance between Earth and the sun, approximately 93 million miles. Venus follows at 7/10. Earth sits at 1 astronomical unit by definition. Mars follows at about 1.5. These 4 rocky planets constitute the inner solar system, a compact zone where solid surfaces and thin atmospheres exist under relatively intense sunlight. Light crosses the entire inner solar system in under 25 minutes. Beyond Mars lies the asteroid belt, a broad ring of rocky debris stretching from roughly 2 to 3.5 astronomical units. Despite its dramatic reputation, the asteroid belt is mostly empty space, a sparse scattering of leftovers from the solar system's formation that Jupiter's gravity prevented from ever coalescing into a planet. Past the asteroid belt, the solar system changes character. Jupiter orbits at 5.2 astronomical units, a gas giant so massive that it contains more than twice the combined mass of every other planet in the solar system. Its gravity shaped the architecture of the entire planetary region, scattering asteroids, deflecting comets, and influencing the orbits of everything nearby. Saturn follows at 9.5 astronomical units. Continue outward past Uranus at 19, and you reach Neptune, the outermost planet, circling the Sun at approximately 30 astronomical units. At this distance, sunlight is 900 times fainter than it is on Earth. Neptune takes 165 Earth years to complete a single orbit. A person born when Neptune was at one point in its orbit would live and die of old age before the planet returned to that same position. And here is where most people's mental map of the solar system ends. Neptune at 30 astronomical units, maybe a few scattered objects beyond it. Then nothing. Blackness. The void between stars. In the popular imagination, the solar system is essentially finished once you pass the last planet. Everything interesting has already happened. The rest is just empty space stretching toward the nearest star, Proxima Centauri, roughly 4.25 light years away. This assumption feels natural. It feels obvious. It also happens to be spectacularly, almost laughably, incomplete. Beyond Neptune lies a region called the Kuiper Belt, a broad disk of icy bodies extending from roughly 30 to about 50 astronomical units from the Sun. The Kuiper Belt is home to Pluto, 39 astronomical units, along with thousands of other frozen remnants from the solar system's formation. It contains at least 100,000 objects larger than 60 miles across, and likely millions of smaller ones. It was not confirmed to exist until 1992, when astronomers David Jewett and Jane Liu discovered the first Kuiper Belt object beyond Pluto. The Kuiper Belt matters because it proves the solar system does not simply stop at Neptune. There is structure beyond the last planet, material orbiting the Sun in organized patterns at distances well beyond the familiar diagram. But even the Kuiper Belt, as significant as it is, only extends the map slightly. 50 astronomical units is still relatively close to the Sun in the grand scheme. Light from the Sun reaches the outer edge of the Kuiper Belt in about 7 hours. The Kuiper Belt is a porch beyond the back door. It hints that the property extends farther than you thought, but it does not prepare you for how much farther. Beyond the Kuiper Belt, the solar system grows stranger. The scattered disk extends from about 30 astronomical units outward to several hundred, populated by objects in highly elliptical orbits flung outward by Neptune's gravity. One such object, the dwarf planet Eris, orbits as far as 97 astronomical units from the Sun at its most distant point. Another, Sedna, follows a spectacularly elongated orbit that swings so far from the Sun and returns so slowly that it occupies a region no known planet can explain. Sedna is important. Its orbit is too distant and too detached from the planets for Neptune's gravity to explain. Something else must have influenced it, either a passing star, the gravitational environment of the Sun's birth cluster, or the tidal pull of the Milky Way itself. Sedna sits in a region sometimes called the inner Oort Cloud, or the detached population, a transitional zone between the known solar system and something far more vast. Its existence whispers that the Sun's gravitational influence reaches much, much farther than the planetary region suggests. Now continue outward, past the scattered disk, past Sedna's lonely orbit. At roughly 120 astronomical units, you reach the heliopause, the boundary where the solar wind, a torrent of charged particles streaming outward from the Sun at roughly 1,000,000 miles per hour, finally loses its battle against the pressure of the interstellar medium. Beyond this point, the solar wind no longer dominates the local environment. Interstellar particles and magnetic fields take over. NASA's Voyager 1 spacecraft crossed the heliopause in August 2012 at a distance of about 122 astronomical units from the Sun. Voyager 2 followed in November 2018 at approximately 119 astronomical units. Both spacecraft sent back data, confirming that they had entered interstellar space, the region where the sun's outflowing material no longer holds sway. This is the boundary that many people understandably mistake for the edge of the solar system. The spacecraft have left the sun's bubble of influence. They are flying through interstellar gas. Surely, the solar system is over. Surely, everything beyond this point belongs to the stars. But here is the critical fact that demolishes that assumption. The heliopause is not a gravitational boundary. It is a plasma boundary. It marks where the sun's wind stops, not where the sun's gravity stops. Gravity reaches far, far beyond the heliopause. The sun is still holding objects in orbit at distances that would take Voyager hundreds of centuries to reach. The heliopause sits at roughly 120 astronomical units. The sun's gravitational dominion may extend to 100,000 astronomical units or more. That is a difference of nearly 1,000 times. Crossing the heliopause and declaring the solar system finished is like stepping off your front porch and declaring you have left your country. And yet that is precisely what happened in the public narrative surrounding Voyager 1. When NASA confirmed in September 2013 that Voyager 1 had crossed the heliopause, the event was reported worldwide with a consistent and deeply misleading framing. Headlines declared that humanity's most distant spacecraft had left the solar system. News anchors described it as the first human-made object to enter interstellar space, which was technically accurate, but the phrasing implied something much larger. It implied that the solar system was behind Voyager now, that it had exited, that the boundary had been crossed, and the journey through our cosmic neighborhood was complete. Millions of people absorbed this narrative and filed it away as settled fact. The solar system ends somewhere around 120 astronomical units. Voyager crossed the line. We did it. Story over. But the story was not over. It had barely begun. What Voyager crossed was the edge of the sun's plasma bubble, the region where charged particles from the solar wind yield to the pressure of interstellar gas. This is a meaningful boundary in heliophysics. It marks a real transition in the local particle environment. But it has nothing whatsoever to do with the sun's gravitational reach, which continues outward for thousands of times that distance without interruption. The heliopause is not a fence around the solar system. It is a change in the weather. The property line is incomparably farther out. The damage done by those headlines is difficult to overstate. They gave an entire generation of casual science followers a mental anchor for the size of the solar system that is off by a factor of roughly 1,000. When people hear that the Oort Cloud extends to 100,000 astronomical units, the number bounces off a wall of prior belief that says the solar system ends at 120. The two numbers cannot coexist in the same mental model without one of them breaking. And the one that usually survives is the one that arrived first, attached to a triumphant headline about a brave little spacecraft leaving home. The comfortable lie was not just taught in classrooms. It was reinforced by one of the most celebrated moments in the history of space exploration. Something is out there, far beyond the heliopause, far beyond Sedna, far beyond anything humanity has ever visited or directly observed, and the evidence for its existence has been arriving in our skies for as long as humans have been watching. Comets. Specifically, long-period comets. Short-period comets like Halley's Comet orbit the Sun in predictable cycles, returning every few decades or centuries. Their orbits are relatively small and tilted only modestly relative to the plane of the planets. Most of them originate in the Kuiper belt or the scattered disk, gravitationally nudged inward by the outer planets until they settle into repeating paths through the inner solar system. But long-period comets are different. They arrive on orbits that take thousands, tens of thousands, sometimes hundreds of thousands of years to complete. They plunge toward the Sun from enormous distances, swing around it in a blaze of vaporizing ice, and then retreat back into the darkness on trajectories so elongated that they will not return for millennia. Some of them are making their first ever visit to the inner solar system since the Sun formed 4.5 billion years ago. Here is what makes them so revealing. Long-period comets do not arrive from one direction. They come from everywhere. Their orbits are tilted at every conceivable angle relative to the planetary plane. Some arrive from above, some from below, some from the direction of Orion, others from the opposite side of the sky. If you plotted their most distant orbital points on a map, they would form not a flat disk like the Kuiper belt, but a sphere, a shell of origin points surrounding the Sun in every direction at distances of tens of thousands of astronomical units. This pattern is not random, it is a signature. It tells scientists that somewhere out there, at distances vastly exceeding the planetary region, there exists a roughly spherical reservoir of icy objects from which these comets are being dislodged and sent tumbling toward the Sun. The reservoir must be enormous to produce comets arriving from all directions. It must be distant to explain their orbital periods, and it must contain a staggering number of objects, because long-period comets keep arriving, century after century, and each one that plunges too close to the Sun and evaporates must be replaced by another from the reservoir to keep the supply going over billions of years. This is not speculation. This is orbital mechanics. The comets are real. Their trajectories are measured. The mathematics demands a source. In 1950, a Dutch astronomer named Jan Hendrik Oort sat down with the orbital data of 19 long-period comets and noticed something striking. When he calculated their aphelia, the most distant points of their orbits, they clustered around a specific range of distances, roughly 20,000 to 50,000 astronomical units from the Sun. The clustering was too tight to be coincidental. It pointed toward a specific structure at a specific distance, a vast cloud of icy bodies orbiting the Sun at the outermost edge of its gravitational reach. Oort was not the first to suspect such a structure. In 1932, the Estonian astronomer Ernst Öpik had proposed a similar reservoir of comets at the solar system's edge, but Oort had the data. He had the orbital statistics, and he had the insight to connect the observed comet trajectories with a physical mechanism that could explain how objects in stable, distant orbits occasionally get knocked out of them and sent plunging toward the Sun. That mechanism was stellar perturbation. Stars do not stay fixed in the sky. They move through the galaxy on their own orbits, and occasionally, over millions of years, a star passes relatively close to the Sun, not close enough to disrupt the planets, but close enough to gravitationally nudge objects at the very outer edge of the Sun's influence. Those nudges can change an icy body's orbit just enough to send it falling inward on a new trajectory, one that eventually carries it past Jupiter, past Mars, past Earth, close enough to the Sun for its ice to vaporize into a glowing tail. A comet is born, and its birth certificate reveals its home address, a region of space so far from the Sun that the boundary between the solar system and the galaxy itself begins to blur. Oort proposed that this reservoir is not a thin ring or a flat disk, but a sphere, a thick shell of icy objects surrounding the entire solar system, at distances thousands of times greater than Neptune's orbit. The structure was eventually named the Oort Cloud in his honour, and in the decades since his proposal, every new line of evidence has strengthened the case for its existence. But here is the part that should unsettle you. When Oort published his paper, the estimated outer boundary of this cloud was somewhere around 50,000 to 100,000 astronomical units from the Sun. Later models push some estimates even higher, to 150,000 or 200,000 astronomical units. Convert those numbers into more familiar units and the result is staggering. 100,000 astronomical units is approximately 1.5 light years. 200,000 astronomical units is over 3 light years. The nearest star to the Sun, Proxima Centauri, sits at approximately 4.25 light years away. This means the Oort cloud, if it extends to its estimated outer limits, may reach a quarter to more than halfway to the nearest star. The solar system does not end at Neptune. It does not end at the Kuiper belt. It does not end at the heliopause. It may extend so far into the darkness between stars that calling it a local, compact, neighbourhood system becomes almost absurd. You thought the solar system was a diagram of 8 planets. It might be a sphere of ice and darkness stretching across light years. Everything you learned about the solar system in school, Every poster, every animation, every neatly labeled diagram showed you only the bright central core of a structure so vast that the entire planetary region is reduced to a pinpoint at its center. The 8 planets, all their moons, the asteroid belt, the Kuiper belt, the heliopause, all of it fits within the first 150 astronomical units or so. The Oort cloud may extend to 100,000 astronomical units, possibly farther. The familiar solar system occupies roughly 0.1% of the Sun's total gravitational domain, maybe less. You are looking at the nucleus of a cell and thinking it was the whole organism. The question now is not whether the Oort cloud exists. The orbital evidence is too strong, the mathematical case too solid, the comet supply too consistent. The question is what it actually looks like, how it formed, how far it truly extends, and what it means for the structure we casually call home. Because if the Oort cloud is real, and virtually every planetary scientist believes it is, then the solar system is not what you thought it was. It is not a compact arrangement of planets bathed in sunlight. It is a tiny ember of warmth surrounded by a vast, dark, frozen sphere of trillions of icy objects, stretching outward into a region so remote that the sun itself is just another dim star in the sky. And that sphere may be so large that its outer reaches already brush against the gravitational territory of other stars. The comfortable diagram lied to you, not through malice, through omission. It showed you the planets because the planets are visible, dramatic, and close. It left out the Oort cloud because the Oort cloud is invisible, silent, and far. But in terms of sheer spatial extent, the Oort cloud does not merely dwarf the planetary solar system, it erases it. The planets become a rounding error inside a structure so large it challenges the meaning of the word neighborhood. What comes next reveals what scientists believe this hidden structure actually is, how its architecture was shaped by forces both solar and galactic, and why a discovery made inside a planetarium dome in 2024 may have just added a twist to the Oort cloud story that nobody expected. No human has ever seen the Oort cloud. No telescope has ever photographed it. No spacecraft has ever come within centuries of reaching it. In the entire history of astronomy, across every wavelength of light we know how to detect, from radio waves to gamma rays, not a single confirmed image of the Oort cloud has ever been captured. And yet scientists are nearly certain it is there, surrounding us right now, extending in every direction into the frozen darkness beyond the planets, containing more individual objects than every star visible to the naked eye, multiplied by a factor of millions. This paradox, an enormous structure that is simultaneously everywhere around us and completely invisible, lies at the heart of understanding what the Oort cloud actually is. Because the Oort cloud is not a solid wall, it is not a dense fog, it is not even a particularly crowded place by any human standard. It is a population, a vast and almost unimaginably sparse scattering of icy objects, drifting through a volume of space so large that even trillions of bodies disappear inside it, like individual snowflakes lost in the atmosphere of an entire continent. To understand the Oort cloud, you need to understand its architecture. Scientists divide it into 2 broad regions, each with distinct characteristics shaped by different physical forces. The inner region is called the Hills Cloud, named after the astronomer Jack Hills, who proposed its existence in 1981. The Hills Cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun, and extend outward to roughly 20,000 astronomical units. Unlike the spherical outer region, the Hills Cloud is believed to be more flattened, shaped like a thick torus or donut concentrated loosely around the plane of the solar system. It is thought to be far denser than the outer cloud, containing perhaps 5 to 10 times as many objects. Some models suggest tens of billions or even hundreds of billions of icy bodies orbit within this inner zone. Yet even here, the distances between individual objects are enormous. You could travel for millions of miles through the Hills Cloud and never pass close enough to any single object to see it with the naked eye. The outer Oort cloud begins where the Hills Cloud fades, roughly beyond 20,000 astronomical units, and extends outward to somewhere between 50,000 and 100,000 astronomical units, with some estimates placing the absolute outer boundary as far as 150,000 to 200,000 astronomical units from the Sun. This outer shell is approximately spherical. Objects within it orbit the Sun at every inclination and in every direction. Some orbit in the same direction as the planets, others orbit in the opposite direction. Some trace paths that are nearly circular at tremendous distances. Others follow highly elongated ellipses that carry them from the outer cloud deep into the inner solar system and back again over timescales measured in millions of years. The total population of the Oort Cloud remains uncertain because we cannot count objects we cannot see, but models based on the observed rate of long-period comet arrivals and the dynamics of how comets are dislodged from the cloud suggest staggering numbers. Conservative estimates place the population at several hundred billion objects larger than about half a mile across. More generous models propose 1 trillion or more. The combined mass of the entire Oort Cloud, despite containing so many objects, is believed to be modest, perhaps a fraction of an Earth mass to as much as several Earth masses depending on the model, though some older estimates ranged considerably higher. This may seem modest, but spread across a sphere potentially light years in radius, it means the Oort Cloud is one of the most diffuse structures in the solar system. Its density is so low that it makes the best laboratory vacuums on Earth look crowded by comparison. The objects themselves are believed to be icy planetesimals, primordial remnants from the formation of the solar system roughly 4.5 billion years ago. They are composed primarily of water ice, along with frozen carbon dioxide, methane, ammonia, and other volatile compounds, mixed with dust and rock. Most are small, probably a few miles across or less, though some could be substantially larger. They are dark, reflecting very little sunlight, which is itself vanishingly faint at their enormous distances. A typical Oort Cloud object receives so little solar energy that its surface temperature hovers just a few degrees above absolute zero, somewhere around 4 to 10 Kelvin. At these temperatures, even gases like nitrogen and carbon monoxide are frozen solid. These are the coldest, most isolated objects in the solar system, drifting through near total darkness in orbits that take millions of years to complete. Why do scientists believe this structure exists despite never having observed it directly? The answer begins with the comets themselves. Long-period comets have been arriving in the inner solar system for as long as humans have been recording astronomical events. These comets follow orbits with periods exceeding 200 years, and many have periods measured in thousands or tens of thousands of years. When astronomers calculate the most distant points of their orbits, the aphelia, a consistent pattern emerges. Many long-period comets have aphelia clustered between roughly 20,000 and 50,000 astronomical units. Others trace paths suggesting they originated from even greater distances. Critically, their orbital planes are randomly distributed. They arrive from every direction in the sky with no preferred orientation, unlike the Kuiper belt objects and short-period comets that tend to orbit roughly in the plane of the planets. This random distribution is the signature of a spherical source region. If long-period comets came from a flat disk, they would arrive preferentially from directions near the ecliptic plane. They do not. They come from above, below, and every angle in between. The only geometry consistent with this pattern is a shell, a vast sphere of source material surrounding the Sun at great distances. The evidence is not abstract. It arrives in our skies with names and dates and precisely measured trajectories, and every new long-period comet strengthens the case for the structure that sent it. Consider Comet Hale-Bopp, which appeared in 1997 and became one of the most widely observed comets of the 20th century. Its orbital period was calculated at roughly 2,500 years, and its aphelion, the most distant point of its orbit, sits at approximately 370 astronomical units. Hale-Bopp is not an outer Oort Cloud object. Its orbit places it closer to the scattered disk and the Hills Cloud transition zone, but its behavior, its pristine icy composition, and its trajectory illustrate the general principle. This comet spent thousands of years in the cold outer reaches of the solar system before gravitational forces redirected it inward, where it briefly became a brilliant spectacle before retreating back into the darkness. Now consider Comet Hyakutake, which passed Earth in 1996. Before its encounter with the inner solar system, its orbit carried it to an aphelion somewhere in the range of 1,000 to 2,000 astronomical units, with an estimated period of thousands to tens of thousands of years, placing its most distant point near the threshold of the inner Oort Cloud. Gravitational interactions with the giant planets during its passage reshaped its trajectory dramatically, stretching its new orbital period to roughly 70,000 years, with an aphelion now reaching approximately 3,400 astronomical units. Hyakutake arrived from a region so remote that when it last visited the inner solar system, modern humans were still hunting across Ice Age landscapes and painting animals on cave walls. It spent millennia drifting through near-total darkness before gravitational forces sent it falling sunward. Then there are comets whose orbital periods stretch to hundreds of thousands or even millions of years. Objects arriving from aphelia at tens of thousands of astronomical units, deep within the territory of the outer Oort Cloud. These are the most direct messengers from the cloud's distant reaches. Each one carries frozen material that has remained virtually unchanged since the solar system formed. Their chemical compositions provide snapshots of the primordial disk from which the planets were born, and their trajectories, arriving from every direction in the sky, confirm the spherical geometry of their source population. Most recently, Comet C 2025 R3 Pan-STARRS, discovered in September 2025 and confirmed by the Minor Planet Center, has drawn attention as another long-period visitor from the outer solar system. Astronomers classified it as a long-period comet with a steep orbital inclination far above the plane of the planets, exactly the kind of trajectory expected from an Oort Cloud origin. The comet reached perihelion in April 2026 at a distance of roughly 47 million miles from the Sun. Its full orbital period remains uncertain because only a short arc of observations exists so far, but it could span thousands of years. Comets like C 2025 R3 arrive regularly, each one a fresh data point confirming that the distant reservoir is still active, still populated, still sending members inward on trajectories shaped by galactic tides and stellar encounters. But comets are not the only evidence for the Oort Cloud. There are objects that never reach the inner solar system at all, yet whose orbits point unmistakably toward the existence of a vast outer structure. Sedna is the most famous of these. Discovered in 2003 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz, Sedna follows one of the most extreme orbits of any known solar system object. Its closest approach to the Sun, its perihelion, is approximately 76 astronomical units, well beyond the gravitational reach of Neptune. Its farthest point, its aphelion, stretches to roughly 937 astronomical units. Sedna takes approximately 11,400 years to complete a single orbit. It exists in a region of space that does not fit neatly into the categories of Kuiper Belt, scattered disk, or classical Oort cloud. It is too close for the outer cloud, and too detached from the planets for Neptune to have placed it there through ordinary gravitational scattering. Sedna's orbit demands an explanation, and the leading candidates all involve forces associated with the Oort cloud's formation. One possibility is that a passing star in the Sun's birth cluster gravitationally tugged Sedna's orbit into its current configuration billions of years ago, during the era when the Sun was still embedded in the dense stellar environment where it formed. Another possibility involves the galactic tide raising Sedna's perihelion during the early stages of Oort cloud formation, effectively parking it in a stable but extremely elongated orbit. A third hypothesis proposes that an as-yet undiscovered massive planet in the outer solar system could have sculpted Sedna's trajectory, though this remains unconfirmed and controversial. Whatever the mechanism, Sedna occupies the transition zone between the known solar system and the inner Oort cloud. It is a boundary object, a physical artifact of the processes that built the cloud itself, And it is not alone. Another object, 2012 VP113, follows a similarly detached orbit with a perihelion of roughly 80 astronomical units and an estimated orbital period exceeding 4,000 years. Additional detached trans-Neptunian objects continue to be discovered, each one populating the same intermediate region and reinforcing the picture of a continuous structure extending outward from the Kuiper belt through the Hills cloud and into the outer Oort cloud beyond. These objects are not members of the Oort cloud in the classical sense. They orbit too close to the Sun for the galactic tide to be the dominant force shaping their trajectories, but they represent the inner edge of the same continuum, the closest and most accessible fragments of a population that extends outward for tens of thousands of astronomical units. Sedna is the tip of a structure so vast that the rest of it vanishes into the darkness beyond our ability to detect. The formation model that best explains how all this material reached its current location has been refined over decades and is closely tied to a broader framework called the Nice model, named after the city in France where it was developed. The Nice model describes a period of dramatic planetary migration that occurred in the first several 100 million years after the solar system formed. In the Nice model, the giant planets originally orbited in a more compact configuration, closer to the Sun and closer to each other than they are today. Beyond them stretched a massive disk of icy planetesimals, containing perhaps 35 to 50 Earth masses. At some point, Jupiter and Saturn crossed a mutual orbital resonance that destabilized the entire outer solar system. Uranus and Neptune were scattered outward into the planetesimal disk, ploughing through it like wrecking balls. This event was catastrophic for the planetesimal population. As Uranus and Neptune migrated outward, their gravitational influence scattered planetesimals in every direction. Some were flung inward, bombarding the inner planets in an episode that may correspond to the Late Heavy Bombardment. Others were scattered outward on highly elongated orbits reaching thousands or tens of thousands of astronomical units from the Sun. Many of these outward scattered objects were ejected entirely, flung beyond the Sun's gravitational reach and lost to interstellar space. But a significant fraction remained bound, their orbits gradually circularized and randomized by the galactic tide and the gravitational influence of the Sun's birth cluster. These survivors became the Oort Cloud. The Nice model explains why the Oort Cloud contains material that originally formed in the region between the giant planets, why that material was scattered to such extreme distances, and why the cloud's total mass is relatively modest compared to the original planetesimal disk. Most of the disk's mass was either incorporated into the planets, flung into interstellar space, or ground down through collisions. Only a small percentage, estimated at 1 to a few percent, ended up trapped in the Oort Cloud. But even that small percentage, drawn from a disk containing tens of Earth masses, was enough to populate a cloud containing trillions of objects. But there is a deeper puzzle. Long-period comets are fragile. Each time one approaches the Sun, solar heating vaporizes some of its ice, producing the spectacular coma and tail that make comets visible. With each orbit, the comet loses mass. After a few hundred passes, a typical comet is destroyed. This means that long-period comets have limited lifespans once they enter repeating orbits, yet we keep seeing new ones arrive. Century after century, new comets appear on trajectories indicating they have never visited the inner solar system before. This steady supply requires a reservoir. If long-period comets were not being continuously replenished from some distant source, the supply would have dried up billions of years ago. The solar system is 4.5 billion years old. Any comet population that was not being restocked would have been destroyed long ago through solar erosion, planetary ejection, or gravitational disruption. The fact that new long-period comets keep arriving proves that a large population of icy bodies still exists at great distances, occasionally sending members inward to replace those that are lost. The mechanism that dislodges these objects from their distant orbits is now well understood, and it involves forces that originate far beyond the solar system itself. The first force is stellar perturbation. the Sun is not isolated. It orbits the galactic center along with hundreds of billions of other stars, and over millions of years other stars occasionally pass through the Sun's general neighborhood. Even a star passing within 1 light year would have a negligible effect on anything inside Neptune's orbit. But at the outer reaches of the Oort Cloud, where objects are only loosely bound to the Sun's gravity, the gravitational nudge from a passing star can be significant. A star passing within a light year or two can slightly alter the orbits of outer Oort Cloud objects, changing their trajectories just enough to send some of them falling inward toward the Sun on new, highly elongated paths. Over billions of years, countless stellar passages have stirred the outer Oort Cloud, continuously dislodging comets and sending them streaming toward the inner solar system. The second force, and in many ways the more fundamental one, is the galactic tide. The Sun sits within the disk of the Milky Way galaxy, surrounded by the combined gravitational influence of hundreds of billions of stars, vast clouds of gas and dust, and an enormous halo of dark matter. This collective gravitational field creates a tidal force that acts on everything orbiting the Sun, but its effects are only significant at extreme distances where the Sun's own gravity is already very weak. For objects in the outer Oort Cloud, the galactic tide is strong enough to systematically change orbital parameters over millions of years. It can rotate orbital planes, increase or decrease orbital eccentricities, and raise or lower perihelion distances, the closest points of approach to the Sun. When the galactic tide lowers an Oort Cloud object's perihelion enough that it begins to interact with the giant planets, the object enters the inner solar system as a new long-period comet. Research over the past several decades has revealed that the galactic tide and stellar perturbations do not merely operate independently. They work together in a synergy first elucidated by astronomers Hans Rieckmann, Mark Fouchard, and their colleagues. The galactic tide systematically evolves the orbits of Oort Cloud objects over long timescales, while passing stars inject bursts of random perturbation that can accelerate the process. This synergy explains why the supply of long-period comets remains relatively steady over time rather than arriving in dramatic pulses. The two mechanisms complement each other, maintaining a continuous trickle of comets from the outer reservoir into the inner solar system. There is a third mechanism that adds another layer. In 2009, astronomers Nathan Kaib and Thomas Quinn demonstrated through computer simulations that comets from the inner Oort Cloud, the Hills Cloud region, can also reach the inner solar system, but through a different pathway. Objects in the Hills Cloud are too tightly bound to the Sun for the galactic tide, or passing stars to directly inject them into the inner solar system. However, gravitational interactions with the giant planets can scatter these objects outward into the outer Oort Cloud, where external forces then redirect them inward. Some arrive disguised as apparently new comets from the outer cloud, even though they originally resided in the inner cloud. The Hills Cloud acts as a hidden reservoir that feeds the outer cloud, which in turn feeds the comet supply, making the Oort Cloud a dynamically evolving system rather than a static one. Understanding where all these icy bodies came from in the first place requires rewinding to the solar system's earliest history, roughly 4.5 billion years ago. At that time, the Sun was surrounded by a massive disk of gas and dust called the protoplanetary disk. Within this disk, solid particles collided and stuck together, gradually building larger and larger objects. The biggest of these became the cores of the giant planets Jupiter, Saturn, Uranus, and Neptune. But the disk contained far more solid material than the planets could absorb. Trillions of smaller icy bodies, called planetesimals, remained as leftovers. As the giant planets grew and migrated through the disk, their powerful gravitational fields scattered these planetesimals in every direction. Jupiter, the most massive, was particularly effective at this. It flung planetesimals both inward and outward with tremendous force. Many were ejected from the solar system entirely, launched on trajectories that carried them out of the Sun's gravitational reach and into interstellar space. But many others were scattered into highly elongated orbits that carried them to enormous distances without quite reaching escape velocity. They remained gravitationally bound to the Sun, orbiting at thousands or tens of thousands of astronomical units on paths that took millions of years to complete. Once these scattered planetesimals reached sufficiently large distances, the galactic tide and the gravitational influence of the Sun's stellar birth cluster began to modify their orbits. The galactic tide gradually raised their perihelion distances, pulling them away from the planetary region and preventing the giant planets from scattering them again. Over hundreds of millions of years, this process decoupled the scattered objects from the planets entirely, trapping them in stable orbits at great distances. They became the Oort Cloud. This formation model, refined through decades of increasingly sophisticated computer simulations, explains several key features of the Oort Cloud. It explains why the outer cloud is spherical, because the galactic tide randomizes orbital inclinations over time, spreading objects into a shell rather than a disk. It explains why the inner cloud is more flattened, because galactic tidal effects are weaker at shorter distances and have not had enough time to fully randomize the orbits. It explains the total mass, because most of the scattered planetesimals were ejected entirely, with only a fraction remaining bound in the cloud. And it explains the ongoing comet supply, because the cloud contains enough objects to sustain a steady trickle of comets over the solar system's entire lifetime. Recent research has continued to refine this picture in important ways. A 2025 paper published in Astronomy and Astrophysics by Simon Porteges, Zwart and colleagues examined the relationship between the Oort Cloud's current mass and the Sun's early history. Their models suggest the Oort Cloud's mass, estimated between roughly 2/10 and 2 Earth masses, is best explained if the Sun departed its parent star cluster within about 20 million years after the giant planets formed. This constrains the Sun's birth environment and links the Oort Cloud's properties to events that occurred at the very dawn of the solar system. But perhaps the most striking recent development arrived from an entirely unexpected direction. In September 2024, curators at the Hayden Planetarium in New York City were preparing a new show called Encounters in the Milky Way. The show included a detailed visualization of the solar system's outer regions, built from simulation data provided by David Nesvorny, a planetary scientist at the Southwest Research Institute who had spent years modelling the Oort Cloud's formation and dynamics. When the team projected the scene onto the planetarium dome, astrophysicist Jackie Faherty noticed something strange in the visualization of the inner Oort Cloud. A spiral, 2 distinct arms, curling outward like a miniature galaxy, clearly visible in the data. At first, Nesvorny suspected an artifact, a glitch in the rendering or a distortion introduced by the visualization software. But when he went back to his raw simulation data, the spiral was there too. He had simply never looked at the data in the 3-dimensional Cartesian coordinates that the planetarium projection used. In his standard analytical framework, the structure had been invisible. Viewed from the right perspective, it was unmistakable. Nesvorny used NASA's Pleiades supercomputer to run additional simulations, testing whether the spiral persisted under different parameters, different stellar encounter histories, and different initial conditions. It did. Every simulation produced the same basic structure: a 2-armed spiral in the inner Oort Cloud, approximately 15,000 astronomical units across, oriented roughly perpendicular to the galactic plane. The physical explanation turned out to be elegant. Objects in the inner Oort Cloud, at distances between roughly 1,000 and 10,000 astronomical units, exist in a region where the Sun's gravity and the galactic tide are both significant forces. The galactic tide, the gravitational influence exerted by the combined mass of stars and dark matter in the Milky Way, acts on these distant objects by slowly rotating their orbital planes and modifying their eccentricities. This process, governed by a phenomenon known as Kozai-Lidov oscillations, does not act uniformly on all objects. Its effects depend on each object's specific orbital parameters. The result is that objects at different distances and inclinations evolve at different rates, creating a systematic twisting pattern. Over billions of years, this differential evolution produces a spiral structure in physical space, with 2 arms winding outward from the inner edge of the cloud. The spiral is remarkably stable, Nesvorny's simulations showed that it formed early in the solar system's history, within the first few 100 million years, and has persisted to the present day. Even close stellar passages, which can temporarily disrupt the outer Oort cloud, leave the inner spiral largely intact because the objects composing it are more tightly bound to the Sun and less susceptible to external perturbation. The discovery was published in February 2025 on the preprint server Argsiv and is now in press at the Astrophysical Journal. It represents a candidate finding, not yet independently confirmed through observation. Directly detecting the spiral would require identifying hundreds of individual Oort cloud objects and mapping their three-dimensional positions, a task that remains beyond current observational capability. The Vera C. Rubin Observatory, which recently began operations in Chile, may discover dozens of individual Oort cloud objects through its legacy survey of space and time, but Nesvorny himself has noted that dozens are not enough. Hundreds would be needed to produce a meaningful visualization of the spiral pattern. Still, the discovery is significant for what it reveals about the Oort cloud's nature. For decades, the standard picture of the inner Oort cloud was a relatively featureless, flattened distribution of icy bodies. The spiral finding suggests that the Oort cloud possesses internal architecture shaped not just by the Sun and the planets, but by the galaxy itself. The Milky Way's gravitational field has literally sculpted the structure of the solar system's outermost region, twisting it into a pattern that resembles, on a vastly smaller scale, the spiral arms of the galaxy that created the force responsible. The inner Oort cloud carries the fingerprint of the Milky Way written into its shape. This discovery also reinforces a deeper point about the Oort cloud's nature. It is not a static, frozen relic. It is a dynamic structure, continuously shaped by forces operating on timescales of millions and billions of years. The galactic tide rotates orbits. Passing stars dislodge members. The giant planets scatter material outward from the inner solar system. Material flows between the inner and outer cloud regions. Comets are sent spiraling inward toward the Sun, where they briefly blaze before being consumed. The Oort cloud is alive in a gravitational sense, responding to the galaxy around it like a membrane, vibrating in response to sound waves too low for human ears to detect. And yet, for all its trillions of inhabitants, the Oort cloud is one of the loneliest places in the solar system. This is the paradox of its population density. Trillions of objects sounds crowded. It sounds like a dense swarm, a thick fog of icy debris filling the space around the Sun. The reality is the opposite. The volume the Oort cloud occupies is so incomprehensibly vast that trillions of objects vanish inside it, like individual grains of sand scattered across the Pacific Ocean. Consider the numbers. If the outer Oort cloud contains roughly 1 trillion objects spread throughout a spherical shell between 20,000 and 100,000 astronomical units, the average distance between any two neighbouring objects is on the order of billions of miles, roughly 10 to 30 times the distance from the Earth to the Sun. That is not a crowded environment. That is a void punctuated by the occasional frozen mountain separated from its nearest neighbour by a gulf comparable to the distance from the Sun to Saturn or beyond. An observer sitting on one Oort cloud body and looking in every direction would see nothing, no nearby companions, no glinting surfaces catching faint sunlight, no sense of belonging to a population at all, just stars and darkness, indistinguishable from any other patch of deep space. The sparsity of the Oort cloud means that collisions between its members are extraordinarily rare. In the inner solar system, asteroids occasionally strike each other, comets break apart from tidal forces, and gravitational interactions are common enough to reshape orbits over millions of years. In the Oort cloud, 2 objects could orbit for the entire age of the solar system, 4.5 billion years, without ever coming close enough to another cloud member to experience a measurable gravitational interaction. Each body exists in splendid isolation, preserved in its original frozen state by the sheer emptiness surrounding it. The Oort cloud is a museum where every exhibit is separated from every other exhibit by millions of miles of vacuum, and no visitor has ever walked through its halls. This sparsity is precisely why the Oort cloud has never been directly observed. Its individual members are small, typically a few miles across at most, and dark, reflecting almost no light. They are separated by gulfs that make detection through any current telescope technology hopeless. You cannot photograph a population whose members are invisible pinpoints scattered across a volume billions of times larger than the space occupied by the planets. The Oort cloud hides not behind a wall of darkness, but behind the mathematics of dilution, trillions of objects rendered undetectable by the sheer volume they inhabit. The evidence for the Oort cloud, taken together, forms one of the strongest circumstantial cases in planetary science. The orbital statistics of long-period comets demand a spherical source reservoir at great distances. The dynamics of galactic tides and stellar perturbations explain how objects are dislodged from that reservoir and sent inward. The formation models explain how the reservoir was populated in the first place, through planetary scattering during the solar system's youth. The mass estimates are consistent with the known efficiency of planetary ejection processes, and now, supercomputer simulations reveal internal structure that matches theoretical predictions about how galactic tidal forces should shape distant populations of small bodies. No single piece of this evidence is definitive on its own, but together they construct a picture so consistent, so mutually reinforcing, and so resistant to alternative explanations that the scientific community treats the Oort cloud's existence as effectively established. It is hypothesized in the technical sense that it has not been directly photographed. But it is not hypothesized in the colloquial sense of being a mere guess. It is a structure whose existence is required by the physics of the comets we observe, the dynamics of the galaxy we inhabit, and the history of the planetary system we call home. What remains is to confront the scale of this structure, to move beyond the architectural description and into the raw numbers, the distances, the comparisons that reveal just how drastically the Oort cloud transforms the meaning of the solar system. Because knowing that the Oort cloud exists is one thing, feeling how far it extends, understanding what that extension implies for the size of your cosmic address, is something else entirely. The architecture is now clear. The question that remains is how large the building actually is, and whether the human mind can hold the answer without flinching. There is a difference between knowing a number and feeling it. You can see that the Oort cloud may extend to 100,000 astronomical units from the Sun and understand the sentence perfectly. The words are clear, the number is specific, but the sentence does not land. It slides past your mind the way a statistic about national debt slides past, technically comprehended but emotionally weightless. The number is too large for your brain to convert into anything resembling experience. This is not a failure of intelligence. It is a feature of human cognition. Your brain evolved to track distances you could walk, territories you could cross in a day. Your ancestors never needed to process numbers requiring scientific notation. When distances exceed a few hundred miles, your mental mapping software begins to approximate. When they reach billions or trillions of miles, it simply gives up, replacing genuine spatial comprehension with a vague emotional label. Very far. The Oort cloud operates at distances where that vague label is dangerously inadequate. To understand what the Oort cloud means for the solar system, you need to feel the scale, not just hear it. And the only way to feel it is to build it up, layer by layer, comparison by comparison, until the structure assembles itself in your mind, and your old mental model of the solar system breaks apart under the weight of what it was always missing. Start with something familiar. The distance from the Earth to the Sun is 1 astronomical unit, roughly 93 million miles. Light covers this distance in about 8 minutes and 20 seconds. If you could drive at 60 miles per hour without stopping, the trip would take approximately 177 years. That is the baseline, 1 astronomical unit. Hold it in your mind. Neptune, the outermost planet, orbits at 30 astronomical units. Light from the Sun reaches Neptune in about 4 hours and 10 minutes. At the same highway speed, driving to Neptune would take roughly 5,300 years. You would have departed before the construction of Stonehenge and still not arrived. This is the outer boundary of the planetary solar system. The Kuiper belt extends to roughly 50 astronomical units. The heliopause, where the solar wind meets the interstellar medium, sits at about 120 astronomical units. These are the last landmarks most people have heard of. Beyond them, the common assumption is emptiness. Now, step into the Oort cloud. The inner edge of the Hills cloud, the denser inner region, is thought to begin at approximately 2,000 to 5,000 astronomical units from the Sun. Take the lower estimate. 2,000 astronomical units. That is already 67 times farther from the Sun than Neptune. In raw distance, 2,000 astronomical units equals roughly 186 billion miles. Light from the Sun takes about 11.5 days to reach this point. At highway speed, the drive would take 354,000 years. But 2,000 astronomical units is only the threshold. It is where the Oort cloud begins, not where it ends. The Hills cloud extends outward to perhaps 20,000 astronomical units. At that distance, sunlight needs about 4 months to arrive. You are now 667 times farther from the Sun than Neptune. The Sun still holds gravitational dominion here, but just barely. From the outer reaches of the Hills cloud, the Sun would appear as an exceptionally bright star, visually indistinguishable from the other bright stars in the sky, except for the fact that your orbit still traces a vast, lazy ellipse around it. Continue outward. The outer Oort cloud begins beyond the Hills cloud and extends to at least 50,000 astronomical units. At this distance, the Sun's light takes approximately 9.5 months to arrive. You are now roughly 4/5 of a light year from the Sun. The Sun still shines as the brightest star in your sky, a brilliant pinpoint roughly as luminous as Jupiter appears from Earth. But it is nothing more than a point, no disk. No perceptible glow on the surfaces around you, no warmth reaching your skin across that staggering vacuum. You are still orbiting the Sun, still gravitationally bound, still technically inside the solar system, but the experience of being in the solar system would be completely unrecognizable. The brightest star in your sky provides no more useful illumination to your surroundings than any other star. Just a sharp, bright point among thousands of dimmer ones, and the faintest gravitational whisper holding you in an orbit that takes millions of years to complete. Now push to the estimated outer boundary, 100,000 astronomical units. This is the distance most commonly cited as the Oort cloud's outer limit, though some models suggest it could extend even farther. At 100,000 astronomical units, you are approximately 1.5 light years from the Sun. Sunlight needs 1.5 years to reach you. The Sun still shines as one of the brightest stars visible, roughly matching Sirius in apparent brilliance, easily found in the sky if you knew where to look. But that bright point delivers no more heat or illumination to your surroundings than Sirius delivers to Earth, which is to say effectively nothing. The Sun is still bright. It is simply no longer a sun. It is a star, one brilliant point among many, offering light you can see but never feel, and you are still inside the solar system. 1.5 light years. Hold that number for a moment. Proxima Centauri, the nearest known star to the Sun, lies at approximately 4.25 light years. If the Oort cloud's outer edge sits at 1.5 light years, then the Sun's domain extends more than 1/3 of the way to the nearest neighbouring star. Some estimates push the outer boundary to 2 or even 3 light years, meaning the solar system might reach halfway to Proxima Centauri, possibly even farther. The space between our Sun and its closest stellar neighbour is not empty interstellar void from edge to edge. A significant fraction of that gap may still belong to our solar system, filled with trillions of icy bodies tracing vast orbits in frozen darkness. This is the point where most people's intuition fails completely. The solar system extending halfway to the nearest star does not compute. It violates the mental model so thoroughly that the brain tends to reject it or reclassify it as exaggeration. It is not exaggeration. It is the direct consequence of the Sun's gravitational reach, which extends far beyond the region where sunlight can warm anything, far beyond the region where the solar wind can blow, far beyond any boundary that feels intuitively like an edge. To make this scale concrete, consider time. NASA's Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object, travelling outward from the Sun at roughly 38,000 miles per hour, or about 3.5 astronomical units per year. As of 2026, Voyager 1 is approximately 165 astronomical units from the Sun. It has been travelling for nearly 49 years and has not yet reached 1/5% of the way to the Oort Cloud's outer edge. At its current speed, Voyager 1 will reach the inner edge of the Oort Cloud in roughly 300 years. It will not exit the outer boundary for approximately 30,000 years. 30,000 years. When Voyager 1 finally leaves the Oort Cloud, the entire span of recorded human history, from the earliest cave paintings to the present day, will have elapsed roughly once during the crossing. The spacecraft will have been travelling continuously for over 30 millennia, and will only then have passed through the Sun's outermost sphere of gravitational influence. The scale becomes even more visceral when you consider not just travel, but communication. Radio signals travel at the speed of light. If humanity ever sent a probe to the inner edge of the Oort Cloud, at roughly 2,000 astronomical units, a command transmitted from Earth would take about 11 days to arrive. The probe's confirmation signal would take another 11 days to return. A simple round-trip exchange, one instruction and one acknowledgement, would span nearly 3 weeks of waiting. Push the probe to the outer Oort Cloud at 100,000 astronomical units, and the delay becomes devastating. A single command would take a year and a half to reach the spacecraft. The reply would take another year and a half to return. 3 years of silence between a question and its answer. If something went wrong, mission controllers would not learn about the failure until 18 months after it happened, and any corrective instruction they sent would not arrive for another 18 months after that. The probe would be on its own in every practical sense, a machine operating in a darkness so remote that even light, the fastest messenger the universe allows, cannot bridge the gap in less than a year. That single number, 30,000 years to cross the Oort Cloud, is perhaps the most effective tool for grasping the structure's true scale. It is not a number that describes the distance to a far-off destination. It is a number that describes the size of the structure surrounding us. Humanity lives inside a gravitational domain that takes 30,000 years to traverse at the speeds of our fastest spacecraft. And the familiar planetary solar system, the part with all the planets and moons and asteroids, the part that fits in the diagram, occupies a region that Voyager has already nearly crossed in less than 50 years. The Oort Cloud is not an extension of the solar system. By volume, the solar system is the Oort Cloud. Everything else is a footnote at the centre. Light, the fastest thing in the universe, fares only somewhat better. A beam of light leaving the Sun would reach Neptune in about 4 hours. It would cross the heliopause in about 17 hours. It would arrive at the inner edge of the Oort Cloud in roughly 10 to 28 days, depending on where the inner edge actually begins. But that same beam of light would need more than a year, possibly a year and a half, to reach the Oort Cloud's outer boundary. The structure is so large that even light takes more than a year to cross it. Compare this to the time light needs to traverse the entire planetary solar system, from the Sun to Neptune and back. That round trip takes about 8.5 hours. The Oort Cloud is more than 3,000 times wider than the distance from the Sun to Neptune. Stated differently, if you could shrink the Sun to Neptune distance down to 1 inch, the Oort Cloud's outer radius would extend to approximately 278 feet, nearly the length of a football field. The entire planetary solar system would fit inside a thimble at the center of a structure stretching across an entire city block. There is another way to feel this, and it involves a project that science teachers have been building with their students for decades. The Scale Model Solar System. You have probably seen one or participated in building one. You place a basketball or a beach ball at one end of a schoolyard to represent the Sun. Then you walk outward, placing smaller objects at scaled distances, a peppercorn for Mercury a few paces away, a marble for Earth a bit farther, a ping-pong ball for Jupiter across the playground. By the time you reach Neptune, represented by a small bead, you have walked perhaps half a mile from the basketball. Depending on the scale you chose, the model is impressive. Students see the vast empty spaces between planets and gain a visceral appreciation for how spread out the solar system is. But every single one of these models ends at Neptune, sometimes at Pluto. Then the teacher claps the dust off their hands, the students walk back to the classroom, and the lesson is over. Nobody extends the model to the Oort Cloud, because doing so would be physically impossible within the boundaries of any school, any campus, any city. Here is why. In a model where the Sun is a basketball and Neptune sits half a mile away, the inner edge of the Oort Cloud would begin roughly 33 miles from the basketball. That is already outside most towns. But the outer edge, at 100,000 astronomical units, would sit approximately 1,600 miles away. In the United States, that is the distance from New York City to Denver. In Europe, it is the distance from London to Moscow. The model that fit comfortably in a schoolyard for the planets would need to stretch across half a continent to include the Oort Cloud. The basketball sun sits on the sidewalk, Neptune is a bead down the road, and the outer boundary of the solar system is in a different time zone. Every schoolyard model ever built has been teaching students the same truncated lesson, showing them the lit core and cutting off the structure before it even begins to reveal its true size. This ratio carries a mathematical consequence that is easy to state and difficult to absorb. Volume scales with the cube of the radius. If the Oort Cloud's outer boundary is more than 3,000 times farther from the Sun than Neptune, then the volume of the Oort Cloud sphere is roughly 37 billion times larger than the volume of the sphere enclosing the planetary solar system. 37 billion times. The planets and moons and asteroids and Kuiper belt objects all reside within an almost inconceivably tiny fraction of the total volume claimed by the Sun's gravitational domain. The entire familiar solar system occupies a share of the Oort Cloud's volume so vanishingly small that no everyday comparison can capture it. Think of it this way. If the Oort Cloud were a sphere the size of Earth, the planetary solar system at its centre would be a sphere roughly 4 kilometers across, a small hill town swallowed inside an entire world. All 8 planets, all their moons, the asteroid belt, the Kuiper belt, every spacecraft humanity has ever launched, every photograph ever taken of a solar system object, all of it fits inside a volume that, relative to the Oort Cloud, is smaller than a village compared to the entire globe. Now reconsider the classroom diagram. That neat row of planets stretching from Mercury to Neptune, the image you have carried since childhood, represents a region of space, so tiny relative to the actual solar system that rendering it to scale would be impossible on any poster that also included the Oort Cloud. If you drew the Oort Cloud as a circle the size of a classroom wall, the planetary solar system at its centre would be smaller than the period at the end of this sentence. Not a small dot. The period, the full stop, that is the entire realm of human space exploration. Every mission, every flyby, every landing, every telescope image, reduced to a punctuation mark inside a sphere that extends to the walls and far beyond. This visual impossibility is why the classroom diagram exists in the first place. There is no way to draw both the planets and the Oort Cloud in a single image that preserves accurate scale. Any diagram that shows the planets large enough to see necessarily truncates the solar system at Neptune, because including the Oort Cloud at the same scale would require a sheet of paper stretching from one end of a football field to the other, with the planets clustered in an invisible speck at the 50-yard line. The familiar diagram is not a simplification. It is a radical amputation, showing you less than 1/billionth of the real structure and asking you to treat it as the whole. One way to internalize this scale is to abandon distance entirely and use a different metric, the fraction of the solar system's total radial extent that each component occupies. Neptune orbits at 30 astronomical units. If the Oort Cloud extends to 100,000 astronomical units, then Neptune orbits at 0.03% of the solar system's total radius. 0.03%. The outermost planet sits so close to the Sun, relative to the full extent of the solar system, that it barely registers. The Kuiper belt, stretching to 50 astronomical units, still sits within the innermost 0.05%. The heliopause, the boundary where the solar wind stops, is at roughly 0.12%. Everything you have ever heard described as the edge of the solar system is within the first fraction of 1% of its actual extent. Now let those percentages sink in. Every mission NASA has ever flown, every planet humanity has ever photographed, every probe that has ever returned data from the outer solar system has operated within the innermost fraction of 1% of the Sun's domain. Voyager 1, humanity's most distant emissary, after nearly half a century of continuous travel at 38,000 miles per hour, has crossed less than 0.2% of the distance to the Oort Cloud's outer edge. New Horizons, at the time of its Arakoth flyby roughly 44 astronomical units out, sat at fewer than 0.05%. Every breathtaking photograph either spacecraft has returned came from a location so close to the Sun, in Oort Cloud terms, that it might as well have been standing on the Sun's surface. Another way to feel this scale is through energy. Sunlight obeys the inverse square law, meaning its intensity decreases with the square of the distance from the Sun. At Neptune's distance, sunlight is already 900 times fainter than on Earth. At the inner edge of the Oort Cloud, it has faded to millionths of its earthly strength. At the outer boundary of 100,000 astronomical units, the Sun's light delivers roughly 1/10 billionth of the intensity it provides at Earth. An Oort Cloud object at that distance receives so little sunlight that the combined glow of distant stars scattered across the galaxy contributes a comparable amount of illumination. Out there, the Sun remains one of the brightest stars visible, but that brightness is a trick of the eye. It carries no warmth across that distance, stirs no weather, melts no ice, sustains no liquid water. It is a beacon with no practical function, a lighthouse whose beam has thinned to nothing long before reaching the ships it was meant to guide. But distance and dimness are only 2 dimensions of the Oort Cloud's strangeness. There is a third that is equally disorienting, and it becomes visible only when you compare the cloud's mass to the volume it occupies. The Oort Cloud, despite containing perhaps 1 trillion or more individual objects, has a total mass that is startlingly small. Current estimates range widely, from as little as a fraction of an Earth mass to as much as several Earth masses, depending on the model and which regions of the cloud are included. Recent work favours the lower end, placing the outer cloud's mass at roughly a few Earth masses or less. That is the combined mass of every single object in the cloud, every frozen mountain, every icy boulder, every primordial snowball drifting through that enormous sphere. All of it together may weigh less than a handful of Earths at most. For context, Jupiter alone has a mass of roughly 318 Earths. Saturn weighs about 95 Earths. Even Uranus, the least massive of the giant planets, weighs roughly 14.5 Earths. The entire Oort Cloud, stretching from thousands of astronomical units out to 100,000 or beyond, spanning light years of space, containing trillions of individual bodies, is less massive than Uranus. It may weigh less than a single ice giant planet. The most voluminous structure in the solar system is also one of the least massive. The entire cloud could be compressed into a body smaller than a single ice giant planet. This mass-volume disparity is unlike anything else in human experience. On Earth, large volumes generally correspond to large masses. A building is heavier than a car. A mountain is heavier than a building. A continent is heavier than a mountain. Our intuition links size to weight, because in everyday life, matter fills the spaces it occupies at roughly consistent densities. Rocks are about as dense as other rocks. Water is about as dense as other water. Things get heavier as they get bigger, because the density stays approximately the same. The Oort Cloud obliterates this intuition. Its average density is so low that expressing it requires scientific notation in the negative direction. If you calculated the average mass per cubic mile of Oort Cloud volume, The resulting number would be so small that it would take many decimal places just to reach the first non-zero digit. The Oort Cloud is not empty in the way that a vacuum chamber is empty. It is emptier. It is emptier than the space between planets. It is emptier than the space between stars in the solar neighborhood. It approaches the emptiness of intergalactic voids, the most desolate regions in the observable universe. And yet it contains trillions of solid objects. They simply occupy so little of the available volume that they might as well not be there at all from a density perspective. This creates a structure that is physically real but experientially absent. If you flew through the Oort Cloud in a spacecraft, you would have no sensory evidence of its existence, no thickening of surrounding material, no increased frequency of particle impacts on your hull, no change in the starfield outside your window. You could cross the entire Oort Cloud from inner edge to outer boundary and never once encounter a detectable object, never once register a gravitational anomaly, never once have any reason to believe you were inside a structure at all. The Oort Cloud is there, confirmed by every line of evidence that comet science can bring to bear, and it is simultaneously nothing, a ghost written in gravity and statistics rather than in matter dense enough to see or touch. This phantom quality makes the Oort Cloud unique among solar system structures. The planets are solid, visible, photographable. The asteroid belt is sparse but contains objects large enough to visit and land on. The Kuiper belt has yielded to direct observation, with thousands of objects catalogued and Pluto explored up close by New Horizons. Even the solar wind, invisible to the naked eye, is detectable through its interactions with magnetic fields and charged particles. The Oort Cloud alone resists all direct observation. It exists in a category of its own, a structure known through its consequences rather than its presence, defined by the comets it releases rather than the body it possesses. And yet this ghost contains more individual objects than the rest of the solar system combined. Every asteroid, every Kuiper belt object, every comet currently in the inner solar system, every moon of every planet, all of them together, represent a population dwarfed by the trillions of icy bodies drifting through the Oort Cloud's vast and nearly empty volume. The most populated structure in the solar system is the one we cannot see. The richest collection of objects is the one that occupies the most desolate space. The Oort Cloud is a paradox built from ice and emptiness, simultaneously full and hollow, real and invisible, ours and unreachable. This means an observer at the Oort Cloud's outer edge would experience the solar system in a way that no human has ever contemplated. The sun would not warm them. It would not illuminate their surroundings. It would not dominate their sky. It would simply pull them, gently, invisibly, through an orbit so vast and so slow that no conceivable lifetime would suffice to detect the motion. They would be orbiting the sun, technically inside the solar system, technically a resident of the same cosmic neighborhood as Earth, and yet their experience would be indistinguishable from floating in the interstellar void between stars. The solar system at that distance is an abstraction, a gravitational fact with no sensory presence whatsoever. Consider one more comparison. The distance from the Sun to the outer edge of the Oort Cloud, approximately 1.5 light years, is roughly 100,000 times the distance from the Earth to the Sun. If you laid out 100,000 one-foot rulers end to end, the resulting line would stretch about 19 miles. Now imagine that the first ruler, the one closest to you, represents the Earth-Sun distance. The first 6 inches of that ruler covers Mercury's orbit. Venus and Earth fit within the first ruler. Mars sits about 1.5 rulers out. Jupiter is at 5 rulers, Saturn at 9.5, Neptune at 30. The Kuiper belt extends to 50 rulers. The heliopause is at ruler 120. The Oort Cloud's inner edge begins somewhere around ruler 2000. Its outer edge is at ruler 100,000. The line of rulers extends for 19 miles. And every planet, every asteroid, every Kuiper belt object, every spacecraft humanity has ever launched, all of it sits within the first 200 feet, a distance you could walk in about a minute. The remaining 19 miles belong to the Oort Cloud, cold, dark, and invisible. a territory so vast that the familiar solar system would vanish into it without a trace. This is the truth the classroom diagram hides, not through deception, but through the simple impossibility of representing these scales on a single page. The 8 planets are real, their orbits are precisely known, their distances from the Sun are measured to extraordinary accuracy. But they represent a structure that is, in terms of spatial extent, cosmically irrelevant compared to the dark sphere that surrounds them. The planetary solar system is the lit stage at the centre of an unimaginably vast, dark, and empty theatre, and the theatre is the solar system. The stage is just where the actors happen to be standing. Every scale comparison, every time-based measurement, every analogy points to the same conclusion. The Oort Cloud does not merely make the solar system larger than expected, it redefines what the solar system is. The entity we call the solar system is not a collection of planets orbiting a star. It is a gravitational sphere of influence, roughly 2 to 3 light-years in diameter, containing trillions of frozen objects in its outer reaches, and a tiny, insignificant cluster of warm, bright worlds huddled around a nuclear furnace at its exact centre. The planets are not the solar system any more than the pilot light is the furnace. They are the smallest, brightest, most visible component of a structure that extends into darkness for distances that take light itself more than a year to cross. And now, a final thought to carry forward. The Oort Cloud's outer boundary does not sit in isolation. At 1.5 to 3 light-years from the Sun, it extends into a region where the nearest star, Proxima Centauri, is only another 1.25 to 2.75 light-years beyond. The gap between our Sun and its closest neighbour may be narrower than you think. The numbers have done their work, the scale has been built. Now it is time to face what that scale actually implies for the line between our star and the stars beyond it, and to confront the possibility that the line may not exist at all. Every map humanity has ever drawn required an edge. The coastline of a continent, the border of a nation, the property line of a yard. Maps work because they have boundaries, clean lines separating what belongs inside from what belongs outside. The human mind craves these boundaries. It organizes reality by sorting things into containers with defined limits. This is my house. That is the street. Beyond the street is the neighbour's property. The world makes sense because the categories have edges. The solar system was supposed to have an edge. For centuries, that edge was implicit in every diagram, every model, every description of our cosmic neighbourhood. The planets orbit the Sun. Beyond the last planet, the solar system ends. Interstellar space begins, a clean line, a clear boundary. Inside is home. Outside is the void. The human mind could hold this structure because it behaved like every other bounded space in our experience. The Oort Cloud destroys this boundary. It does not blur it slightly. It does not push it outward to a new, farther location where a clean line can be redrawn. It eliminates the concept of a boundary entirely. The Oort Cloud reveals that the solar system does not end. It fades. And the region across which it fades is so vast, so gradual, and so interpenetrated with the forces of the wider galaxy that no line can be drawn anywhere along its length without being arbitrary in a way that strips the line of real meaning. To understand why, you need to look at what happens at the Oort Cloud's outermost reaches, the region where the Sun's gravitational authority begins to dissolve. At the centre of the solar system, the Sun's gravity is overwhelming. Mercury orbits at 36 million miles, completing a loop in 88 days. Moving outward, that grip weakens. Neptune, at roughly 2.8 billion miles, takes 165 years to complete a single orbit. The Sun still holds Neptune firmly, but the leash is longer and the pace is slower. In the Oort Cloud, the leash becomes gossamer. At 50,000 astronomical units, an icy body orbits the Sun once every 10 million years or more. Its orbital velocity is measured not in miles per second, but in fractions of a mile per hour. It drifts. The Sun's gravitational pull at that distance is not zero, but it is so weak that other forces begin to compete with it on nearly equal terms. The most important of those competing forces is the galactic tide. The Milky Way galaxy contains roughly 200 to 400 billion stars, along with vast quantities of gas, dust, and dark matter, all distributed in a disk and halo structure through which the Sun orbits. The combined gravitational influence of this galactic mass creates a tidal field that acts on everything within the galaxy, including the outermost objects orbiting our Sun. For the planets and for objects in the Kuiper belt, the galactic tide is negligible compared to the Sun's gravity. It exists technically, but its effects are unmeasurably small relative to the Sun's dominant pull. But as you move outward through the Oort Cloud, the Sun's gravity weakens while the galactic tide remains constant. At some critical distance, the two forces become comparable. Beyond that distance, the galaxy's gravitational influence exceeds the Sun's. Objects can no longer maintain stable orbits. They are stripped away, claimed by the Milky Way, lost to interstellar space. This transition distance is sometimes described using the concept of the Hill sphere, the region around any orbiting body within which its gravity dominates over the tidal forces of the larger body it orbits. For the Sun, orbiting the center of the Milky Way, the Hill sphere has a radius of roughly 1 to 2 light-years. This radius roughly corresponds to the outermost estimates of the Oort cloud's boundary, which is not a coincidence. The Oort cloud extends as far as the Sun's gravitational authority allows, and no farther. Its outer edge is defined not by any intrinsic property of the cloud itself, but by the point at which the galaxy takes over. But this transition is not a wall. It is not a line. It is a gradient. There is no distance at which the Sun's gravity suddenly drops to zero and the galaxy's tidal force suddenly activates. Both forces operate continuously at every distance. What changes is their ratio. Close to the Sun, solar gravity overwhelms the galactic tide by factors of billions. At Neptune's distance, the ratio is still enormous. At the inner Oort cloud, the Sun still dominates, but the galactic tide has grown strong enough to sculpt orbits over millions of years. At the outer Oort cloud, the two forces are in rough balance, and the Sun's hold on individual objects becomes tenuous, contingent, uncertain. Some objects at these distances are bound, others are not. The difference depends on the specifics of each object's orbit, its velocity, its direction, and the particular gravitational perturbations it has experienced from passing stars over the last 4.5 billion years. This means the outer edge of the solar system is not a boundary in any physical sense. It is a probability distribution. The fraction of objects that are gravitationally bound decreases gradually with distance, from nearly all at the inner Oort cloud to essentially none where the galactic tide has swept everything away. There is no point where you cross from inside to outside. There is only a vast transitional region where belonging to the solar system becomes progressively less certain, less stable, less meaningful. An object at the outer edge of the Oort cloud does not know it is in the solar system. It has no awareness of the Sun as anything special. The Sun is a distant star, one of many, exerting a gravitational pull barely distinguishable from the combined pull of everything else in the galactic neighborhood. The object's orbit is not a clean ellipse. It is a wobbling, precessing, chaotically perturbed trajectory that may remain bound to the Sun for another billion years or may be dislodged by the next passing star and sent drifting into interstellar space. Its allegiance to the solar system is provisional and temporary, a gravitational accident that could be undone by any sufficiently close encounter. And close encounters are not rare. 2007. The Sun moves through a population of stars, each following its own galactic orbit, and over millions of years, some pass close enough to perturb the outer Oort cloud significantly. On average, a star passes within roughly 3 light-years of the Sun every 100,000 years or so. Most passages are distant enough that their effects are minor, but occasionally a star passes much closer. The most dramatic upcoming encounter astronomers have identified involves a star called Gliese 710, a small orange dwarf currently about 64 light-years away. Based on precise measurements from the Gaia spacecraft, Gliese 710 is heading almost directly toward the Sun. In approximately 1.3 million years, it will pass deep into the inner Oort Cloud at a distance of roughly 10,000 astronomical units from the Sun, possibly closer. At that distance, well within the denser Hills cloud region, its gravitational influence will be significant enough to disrupt the orbits of millions or billions of Oort Cloud objects. Some will be flung outward, lost to interstellar space forever. Others will have their orbits deflected inward, their perihelion distances lowered enough that they begin falling toward the inner solar system. Over the following few million years, the inner solar system will experience a shower of new comets, visitors dislodged from the Oort Cloud's outer reaches by the gravitational handshake of a passing star. This is not a catastrophic or unusual event, it is routine. Over the 4.5 billion years of the solar system's existence, hundreds or thousands of stars have passed through or near the Oort Cloud. Each passage stirred the population, ejecting some members, redirecting others, and feeding the comet supply that delivers long-period comets to our skies. The Oort Cloud has been continuously shaped by these encounters, losing members to the galaxy while the galactic tide and planetary scattering replenish it from the inside. It is not a sealed vault. It is an open system, exchanging material with the galaxy in a slow, continuous commerce that has been operating since the solar system formed. This exchange raises a profound question. If the Oort Cloud is constantly losing objects to interstellar space and potentially capturing objects that originated around other stars, where does the solar system end and the rest of the galaxy begin? Consider the possibility that some objects currently orbiting in the Oort Cloud did not form around our Sun at all. The Sun was born in a stellar nursery, a dense cluster of young stars formed from the same collapsing molecular cloud. During the first tens of millions of years, these sibling stars were close enough that their protoplanetary disks and scattered debris could have interacted. Planetesimals flung outward by one star's giant planets could have been captured by a neighbouring star's gravity. Computer simulations of this process suggest that a meaningful fraction of the Oort Cloud's population may consist of objects that originated around other stars in the Sun's birth cluster, captured during those early, crowded years before the cluster dispersed. But the exchange of material between stellar systems is not confined to the distant past. It is happening now, and we have proof. In October 2017, astronomers at the Haleakala Observatory in Hawaii detected an object moving through the inner solar system on a trajectory that was unmistakably interstellar. Its orbit was hyperbolic, meaning it was not gravitationally bound to the Sun. It had entered the solar system from outside, swung past the Sun, and was on its way back out, never to return. The object was named Oumuamua, a Hawaiian word meaning scout or messenger from afar. It was the first confirmed interstellar object ever detected, passing through our solar system. Oumuamua was small, estimated at a few hundred meters across, and its exact nature remains debated. It showed no visible coma or tail, leading some researchers to classify it as an asteroid rather than a comet. Others noted a slight anomalous acceleration as it departed the inner solar system, consistent with outgassing from volatile ices that could have been hidden beneath a surface crust. Its origin star is unknown. It could have been ejected from any planetary system in the galactic neighbourhood millions or billions of years ago, drifting through interstellar space until it happened to pass through our solar system's gravitational domain. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered a second interstellar visitor, now known as Comet 2-1/Borisov. Unlike Oumuamua, Borisov was unambiguously a comet. It displayed a clear coma and tail, confirming the presence of volatile ices vaporizing as it approached the Sun. Its chemical composition was broadly similar to solar system comets, suggesting that the processes of planetary formation and planetesimal scattering that built our Oort Cloud operate similarly around other stars. Borisov was a piece of another star's Oort Cloud, ejected from its home system long ago and wandering the galaxy until chance brought it through ours. These two detections are almost certainly the beginning, not the end, of interstellar object discovery. Statistical models based on the detection rate of Oumuamua and Borisov suggest that at any given moment, there may be thousands of interstellar objects larger than 100 meters passing through the volume of space inside Neptune's orbit. The solar system is not sealed off from the galaxy. It is permeable. Objects from other stars' Oort clouds are constantly drifting through our territory, and objects ejected from our Oort cloud are drifting through theirs. This means the boundary between our solar system and the rest of the galaxy is being physically crossed in both directions continuously by solid objects carrying material from foreign planetary systems. The interstellar medium is not empty. It is populated by a diffuse rain of icy and rocky bodies ejected from countless Oort clouds around countless stars, forming a background population of galactic wanderers that passes through every stellar system in the Milky Way. Our solar system breathes in material from other stars and exhales its own material into the galaxy. The Oort cloud is both the lung and the membrane, the structure through which this exchange occurs. Oumuamua and Borisov did not merely confirm the existence of interstellar objects. They confirmed that the galaxy is a connected system, with material flowing between stars across timescales of millions and billions of years. The boundary of the solar system, already made ambiguous by the Oort cloud's gradual fading into the galactic gravitational field, is further dissolved by the physical reality of matter crossing it in both directions. The solar system is not a closed container. It is an open harbour in a galaxy-wide ocean, and the Oort cloud is the shoreline where the tides of interstellar space wash in and out. If this is true, then the Oort cloud already contains material from other solar systems. Our solar system's outermost structure is not purely ours. It is a mix of local debris and imported material, blended together over billions of years into a population that owes its existence to both the Sun and the wider stellar community. The boundary between our system and others was breached at the very beginning. It has never been sealed since, and the exchange may continue. If the Oort cloud extends to 1.5 or 2 light-years from the Sun, and Proxima Centauri sits at 4.25 light-years, then the gap between the Sun's outermost gravitational territory and the nearest neighbouring star is only about 2 to 3 light-years. If Proxima Centauri possesses its own cloud of distant icy debris, which is entirely plausible given that Oort cloud-like structures are predicted to be a common outcome of planetary formation, then the outer edges of the two clouds may approach each other across the intervening space. They may not physically overlap in any dense or detectable way. The objects are far too sparse for that, but the gravitational spheres of influence begin to nest against one another, with only a relatively narrow no-man's land between them. In this picture, the space between stars is not a vast empty desert with isolated oases of planetary systems scattered through it. Instead, each star sits at the centre of an enormous gravitational domain, its territory extending outward until it meets the territory of its neighbours. The interstellar medium is partitioned into overlapping, competing, fading zones of gravitational influence, with no clean gaps between them. You do not leave one solar system and then travel through empty space before arriving at another. You leave one star's fading grip and almost immediately enter the growing influence of the next. The galaxy is not a collection of isolated stars. It is a mosaic of overlapping gravitational territories, each one defined by an outer shell of icy debris, slowly orbiting a distant point of light. This realization transforms the meaning of the word home. When most people say they live in the solar system, they imagine a compact neighbourhood of planets centred on a warm star, surrounded by empty darkness. The Oort cloud reveals that home is something far larger, far colder, and far stranger. Home extends for light years in every direction. Home is mostly dark. Home includes trillions of frozen objects that no human eye has ever seen, and no human-made instrument has ever detected. Home is a territory so vast that light takes more than a year to cross it. Home includes regions where the sun is just another bright point in a crowded sky, offering light but no warmth. Home reaches so far into the darkness between stars that it begins to blend with the territories of neighbouring suns. And home is not stable. It is being eroded. Every passing star tugs at its edges. The galactic tide rotates and reshapes its outermost structures over millions of years. Objects are continuously lost to interstellar space and occasionally replaced by new captures or by material scattered outward from the inner solar system. The Oort Cloud you inhabit today is not the same Oort Cloud that existed a billion years ago. Its population has churned. Its members have been exchanged. Its boundaries have shifted in response to every stellar passage, every galactic tidal cycle, every gravitational perturbation from the wider Milky Way. The solar system is not a permanent structure. It is a process, an ongoing negotiation between the Sun's gravity and the galaxy's influence, with the Oort Cloud as the contested territory where that negotiation plays out. This impermanence applies to the future as well. The Sun will continue orbiting the galactic center, passing through regions of varying stellar density, encountering molecular clouds, and experiencing tidal forces that change as its position within the galactic disk shifts over hundreds of millions of years. Each new environment will reshape the Oort Cloud differently. In dense stellar regions, close encounters will strip more objects from the outer cloud, shrinking the solar system's effective boundary. In quieter regions, the cloud will relax and spread outward. The solar system breathes, expanding and contracting over galactic timescales in rhythm with its journey around the Milky Way. But the breathing has not been symmetrical. The Oort Cloud we inhabit today is almost certainly a diminished remnant of a structure that was once considerably larger. Galactic erosion has been stripping outer members for billions of years. Every stellar passage that dislodged comets inward also flung others outward into interstellar space, permanently reducing the cloud's population. The galactic tide has been steadily peeling away the most loosely bound objects at the outermost fringe, transferring them from solar orbits to galactic ones. Models of Oort Cloud evolution suggest that the cloud may have lost a significant fraction of its original population over the solar system's lifetime, with some estimates indicating that the current mass represents only a portion of what existed shortly after formation. This means the solar system's outer boundary has been quietly retreating for billions of years. The domain our Sun claimed when the Oort Cloud was young and freshly populated was larger than the domain it claims today, and the erosion continues. 2 billion years from now, the Oort Cloud will be thinner, sparser, and its effective outer edge will have crept closer to the Sun. The solar system is not only boundaryless in space, it is shrinking in time. The home we cannot fully map is also a home we are slowly losing. And what of humanity's relationship to this structure? We have spent 6 decades exploring the solar system with robotic spacecraft. We have visited every planet. We have landed on moons and asteroids and a comet. We have sent probes past the heliopause into interstellar space. But everything we have done, every achievement of the space age, has occurred within the innermost fraction of 1% of the solar system's true extent. The Oort Cloud lies beyond our reach by a margin so enormous that no technology currently imagined could close it within human lifetimes. Even at the speed of light, reaching the outer Oort Cloud would take 1.5 years. At achievable spacecraft velocities, the journey requires millennia. This means the overwhelming majority of the solar system will remain unexplored for the foreseeable future. Not for decades, not for centuries, for timescales that may exceed the duration of human civilization. The Oort Cloud is ours in name only. We claim it as part of our cosmic address, but we cannot visit it, cannot photograph it, cannot study it directly. We know it exists because of the comets it sends us, messages in frozen bottles lobbed inward from a shore we cannot see. And yet the Oort Cloud is not merely a distant abstraction, it is the structure that defines the true size of our cosmic home. Without it, the solar system is a compact cluster of planets a few light hours across, a neat and comprehensible neighborhood. With it, the solar system becomes a diffuse, light-years-wide gravitational empire, mostly dark, mostly empty, mostly unknown, extending into regions that feel emotionally and experientially indistinguishable from the void between stars. This is the true shock of the Oort Cloud. It is not that the solar system contains a distant belt of icy objects somewhere past Neptune. It is that the solar system is not what we thought it was. The structure we call home is not the bright, orderly arrangement of planets that fits on a classroom poster. It is a vast sphere of gravitational influence stretching across light years, with a tiny, luminous core at its center, and an enormous, invisible, frozen outer domain that constitutes virtually all of its volume. The familiar solar system, the one with Mercury and Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune, the one you learned as a child and carry in your mind to this day, is a miniature, a detail, a bright decorative element at the exact center of something incomprehensibly larger. And perhaps the most unsettling realization of all is this. Even before humanity reaches another star, even before we send a spacecraft to Proxima Centauri or detect a signal from an alien civilization, we must first confront the fact that our own star's domain is already larger than we can emotionally accept. The journey to another solar system does not begin at the edge of the planetary region. It does not begin at the heliopause. It begins at the far side of the Oort Cloud, a boundary so distant that reaching it represents a challenge of the same order of magnitude as reaching the nearest star itself. The first great barrier to interstellar travel is not the distance between stars. It is the distance across our own backyard. The Oort Cloud is the solar system's final confession. It admits that the neat, bounded, knowable neighborhood we imagined was always a fiction of convenience. The real solar system is not neat. It is not bounded. It is not knowable in any complete sense. It extends into a darkness so deep and a distance so extreme that it becomes indistinguishable from the darkness between stars. The place you call home already reaches into the abyss. It always has. You just never looked far enough to see it. Somewhere out there, right now, a frozen body the size of a mountain is drifting in absolute darkness at a distance of 70,000 astronomical units from the Sun. It has been orbiting for 4 billion years. It has never been warmed. It has never been photographed. It has never been touched by any instrument or signal from Earth. It belongs to the solar system, held by the Sun's gravity in an orbit that takes roughly 18 million years to complete. From its surface, if surface is even the right word for a body that cold, the Sun is still the single brightest star in the sky, outshining even Sirius, yet it is nothing more than a sharp point of light that provides no heat, casts no shadow, and illuminates nothing. The constellations from that vantage point are almost identical to the ones seen from Earth, because the body is still too close to the Sun, relative to the distance of other stars, for the stellar patterns to shift appreciably. That object is inside your solar system. It is part of your cosmic home. And it orbits in a place so remote, so cold, so dark, and so silent that it already inhabits the emptiness between stars in every way that matters to human experience. The only thing connecting it to your world is an invisible thread of gravity extending across trillions of miles of vacuum. A thread so thin that the next passing star might sever it entirely, sending the object drifting into the interstellar medium to wander the galaxy alone for eternity. That is the true scale of the Oort Cloud. Not a belt, not a wall, not an edge. A fading whisper of gravitational belonging, stretching outward from a warm star into a cold galaxy, growing thinner and quieter with every mile, until the whisper becomes indistinguishable from silence and the solar system dissolves into the night between the stars.